So my name is JF. I'm going to talk to you about star car star 0 equals 0, semicolon. So first we're going to get just rid of the lawn chairs and whatever, put a nicer font. And I'm going to talk a bit about what this talk is about. I got a lot of requests during the week to spoil what the talk was about, and I refused to do so. So my name is JF. I work at a company called Woven by Toyota. I'm chief architect there. I'm also chair of the WG21 C++ evolution working group, so the evolution of the C++ programming language. And so today, I want to give you a talk about a interview question I've asked more than 100 times to different interviewers over time, or interviewees over time. And it's a question that's fairly benign, seems simple. And what's interesting, it's a question that really doesn't have a right answer. It's a very open-ended question. And it's a question that I found for systems engineers and compiler engineers primarily to be fairly revealing of where the boundary of their knowledge is, which is useful, right? Trying to figure out, well, I'm trying to hire a candidate of a particular seniority or a particular bend or whatever. Where do they end up in that series of knowledge? And I end up learning stuff from asking that question as well, so it's always interesting. And it's a good way to get someone talking about something they should know fairly well if they're in the compiler space or system space. And either use it as an icebreaker, talk about it for 5 minutes, or use it as a whole interview slot for a whole hour or something like that. So what I'll do today is I'll pretend to be answering the question for all of you. I made the content fit inside of an hour, so there could be more content than this. So if you're listening on YouTube and you're really upset that I didn't mention a thing, just put it in the comments or something. Like and subscribe, it's always good. And so here's the question. I'll write this on the whiteboard. This isn't my handwriting. This is an actual programming font, but usually I'll go on the whiteboard and write this down. And I'll just say, int main, parens, curly brace, star car star 0 equals 0, semicolon, return 0, semicolon, curly brace. Just talk to me about this code. This is the whole question. Right? And I give him a bit of introduction. I'm like, there's no right or wrong answer. I want to have a discussion about what the code is. Right? And you can take it in any direction. I've asked this question a lot. I don't try to just put people on the spot for fun. Not that just for fun. And so I put this on the whiteboard, and then I ask the person, just start somewhere, right? Start wherever you want. And this can go in many directions. There's what, 1, 2, 3, 4 lines of code plus a new line at the end, so there's like 5 lines of code. It can go in a lot of directions with all those 5 lines that we have. And so I'll start and I'll be like, let's just think about what this is. What does that actually mean? What are you trying to do? Well, today I'll just start by focusing not on the big text, but on the other stuff, right? Like I'm on the standards committee. I know about these things. Let's talk about it. So I'll start and I'll say, well, this is main and knowledge sharing. It can't be inline, can't be static, can't be const expr, can't be extern-C. It has to be C++ linkage. And then I'll say, well, it can't be deleted. That's also something the standard says. And it can't be a coroutine also. Did you know that main can't be a coroutine? It's fun. And then you'll say, well, okay, there's main. Main is the single main function. It's the main entry point. And calling main in C++ is disallowed. You can't, from your program, call main. You can in C, though. That's a fun fact. You can call main from C. And then you have a curly brace there, which is wonderful. And you say, this is the main entry point. And the global constructors, so your globals outside of main, happen before this. And then you say the signature of main could be different, right? Not just parens, but it could be something like int argc and argv. And I forgot a star there, so sorry for the typo. But it could also be something like it's implementation defined what else you have as signatures. So on Apple platforms, it also has envp and star apple in there. Or if you're in freestanding implementations, it could just be whatever. You don't have to have a main in a freestanding implementation, which is also fun. So there's interesting stuff to be had here. And then you say, this is the normal program termination, which calls exit with, in this case, 0, because I passed 0 here, but it'll pass whatever this value here is to exit. And this return 0 is implicit, so you can omit it from main, and that would be totally fine as well. It would return 0 for you. And after that, you have a curly brace. Now, the curly brace just calls the global destructors after it. It's the best garbage collector ever. It's really wonderful. So that's the code, right? I've finished the interview. We've gone 5 minutes. Good. Do I get the job? Well, we can talk about other stuff, but I'm gonna guess you were asking about not the stuff around it, right? It's interesting. It's interesting to share, but I'm gonna guess you're asking about other stuff there than just the main. What other parts of the program should we talk about? Maybe the stuff I've grayed out. Yeah, let's talk about that. So let's focus on this part here. First things first, it's terrible code. I know Matt Godbold here likes it. He's told me many times this week that he likes it. But most people have told me, why would you write a talk with this title? It's terrible. Like, it's cringeworthy. Okay, well, let's break it down. This is an assignment, right? So you're assigning the value 0. That's nice. You're assigning it where? Where you're going to take this, which happens to be a character pointer, and then what are you going to do? Well, you're going to have my clicker that doesn't work, which is annoying. There we go. Add an address cast from integer 0 that you dereference. That's pretty nice. Okay, that's pretty straightforward. So what is that? Well, and then you have the statement end, right? So what does that actually mean, this whole thing? Well, it's a null pointer dereference, right? That's just what it is. I think we agree on that, yeah? Any objections? No? So then, like, it's undefined behavior, right? I think we agree on that. And then the next question is this one. Why would you do that? But it's a good question, right? Like, the whole question I asked was, talk to me about this code, right? And it's fine to ask a question back at me like, why would you do that? And then maybe you should think about why would you do that? That's a good question, actually, right? So maybe the next question I'll have is like, how does this code make you feel? Right? Like, the question isn't necessarily about the code. I just said, talk to me about the code. And how does it make you feel? Well, the people who asked me, why would you give a talk with this title? Some of you showed up, so I think you feel, maybe you were in denial or at the beginning when you asked me, why would you give this talk with this title? And then I wouldn't answer, so you were angry, right? But then you said, come on, please tell me. And then, stuff happened. You went to other talks. You saw Bryce's talk earlier. You've been depressed, honestly. But then you accepted the star car stars equals 0 semicolon, and you came to the talk anyways, or at least some of you did. All right. But like, the real question that I think you should ask yourself is, what did the author expect when they wrote this? Right? There's a variety of reasons why you would write this besides just trying to have fun with the interviewee. You could want a null pointer dereference, legitimately not know that this is undefined behavior, and you wanted a null pointer dereference. You might want a valid write, and I'll get into that later. This might be your objective. You want to write to address 0. That's completely a valid reason to want to do this. It's invalid per the C++ spec, but your feelings are that you wanted to do this, and you wrote it with valid intent, and I want to honor that. You might have wanted a trap. I know Matt Godbold told me that was, what, on Sega you used to do that? Yeah, okay, so you used to use that as your breakpoint, yeah. But he wanted that, that's fine. You might want to have this optimized to no code, and in fact, if you feed this to Clang with optimization set at 02, it removes the code. It just gets rid of it, whereas GCC, in some settings, puts a trap instead, right? So that's maybe what you wanted. Maybe you wanted to write this and get questions to see if the code reviewer was actually paying attention. Maybe that's what you wanted. I don't know. Maybe you just wanted to have fun. I mean, you're all here seemingly having fun, so maybe that's what you wanted to do. Plenty of other reasons you might have expected to write this, right? So when I said, talk to me about this code, it is really like, talk to me about it. What's the purpose? What do you think? Do you really want to have fun? Well, this is a C++ conference, right? It's called C++ on C. The C part is SCA, so not the C letter. So we should talk about, this is more of a C code. Maybe we should make this into C++ code, right? Nice, nice. Okay, so anyone want to say something about this? This is much better, obviously, right? Previous code compiled, does this compile? No, it doesn't compile. It just doesn't compile. I'm just kidding with you. What's the diagnostic? Squigglies. Yeah, that's not allowed. Except the underscore one, and it's just funny. And it's not all the versions of Clang or GCC that do this, right? But it's the libc++ namespacing has it in underscore. I just thought it was funny when it gave it to me, so I just kept it there. But it's just not allowed to cast null pointer to char star. All right, cool. What do we do about this? Because we're trying to have fun. I think we're in the last section here. What are we going to do? Well, I could do this instead, right? So we're going to go with C++20, right? So I'm going to bitcast null pointer to char star. And if you're not familiar with bitcast, it's a function that's kind of as if by memcopy. So you're going to memcopy null pointer into a char star. That's what the spec of bitcast does, effectively. It works at const per time. It's wonderful. It doesn't slice bread, but it does a lot of stuff for you. Much better code. Any objections to it? No, it's wonderful. Cool. Okay. I lied again. It doesn't compile. Why doesn't it compile? Oh, indirection of non-volatile null pointer will be deleted, not trap, and that makes you sad. The compiler's pretty smart. It's a warning, right? So it does compile, but then it says consider using underscore built-in trap or qualifying pointer with volatile. Built-in trap and volatile? What is this? Just ignore this. Now, it is just a diagnostic, and I want to be honest with you. I lied. I just lied. But you could also tell it to go away with f no delete null pointer check. So you could tell it no, just don't delete null pointer checks, it will stay there. But I lied. This doesn't work. Because what I actually did to get this diagnostic is I did underscore built-in bitcast with char star null pointer. Now, I was laughing at the underscore built-in earlier, and now I'm using it myself, right? So the way bitcast is implemented is as if by memcopy, but it has to be const expr, and the way you make it const expr is with a built-in, right? So the way bitcast is implemented is with a built-in. I have an implementation on GitHub from the bitcast standardization times that does all of the stuff except const expr, and you can kind of do it without using const expr, but you can't do the const expr without the built-in. So bitcast in the standard library is implemented with a built-in and GCC and Clang at a minimum. And what's interesting is this a function? What is it? Because it's taking a char star and null pointer. That's the return type, the thing that went in angle braces, right? And the null pointer is the parameter. So what's great when you're a compiler author is you can just make stuff up. And when you create built-ins, you can pass types as parameters to functions. Did you know? It's really fun. You can do all this stuff. And when you do this, it gives you the diagnostic that I gave you earlier, right? Now, I just said that bitcast in the standard library is implemented with built-in bitcast, right? So let's look at what that looks like, because I have questions, right? So this is what it looks like in the standard library. And there's stuff over it. It's pretty straightforward. It actually uses concepts, which is beautiful, right? As requires, and it has to be same size, trivially copyable on both sides. Const expr, bitcast, to, from, no except, and it returns the thing, right? Fairly straightforward, it's beautiful. Let's put a frame around it. Now, I said that when you call bitcast directly, you get the diagnostic that says you're going to do a null pointer dereference, but when it goes through the standard type library, you don't get that diagnostic. Now, I've still passed null pointer to it, and I don't get the diagnostic. Why is that? Anyone? It's a compiler bug. And I haven't filed the bug, because as I was writing the talk, I did that, and I ran into the bug, and I'm like, well, the problem, and I think I know where it is, so whatever Clang developer gets the bug, I'm sorry, but the reason I think is the way the diagnostics work in Clang is when you emit the diagnostics, there's two phases, one for the templates and one for the non-template stuff. And the diagnostic opts in to be relevant for the first phase in templates or not, and I think this one doesn't, and so you don't get the diagnostic. That's my guess of what the problem is. I didn't look at the sources, that's just my guess of what it is. It's just changing a false to true somewhere, adding a parameter somewhere, and then it's fixed. So if anyone wants to file the bug, thank you, that'll be great. I was just too lazy to do it. But that's how stuff works under the hood, right? So let's go back to our call of built-in bitcast, which we found really beautiful. And it was saying this, right? So it's still just a warning, but I want to get rid of it. How do I get rid of it? Any ideas? Turn off, well, no, without turning off the warnings. Okay, you'll love this. You'll love this. You ready? Okay, it's gonna be amazing. 3, 2, 1. Oh, 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 it's awesome. So what did I do, right? So I changed the null pointer to a 0, which obviously gives me the same diagnostic. I skipped that step, but then I made it -0. Now, you'll remember that in C++, integers, signed integers are 2's complement, right? So -0 is just not a thing, right? But that removes the diagnostic. Now, one thing I want to point out is I was using null pointer earlier, and technically null pointer doesn't contain a value because it's a monostate type. And so mem copying from null pointer in my mind just shouldn't be really copying anything. It's a placeholder for no value being there for a pointer. It's not actually a value itself, whereas 0 is totally a value, and so is -0. Now, why don't I get the diagnostic for -0 when I get it for 0? Any guesses? Compiler bug, thank you. Thank you, I haven't filed that one either, but it's great. And so I think, this is a guess for the great Clang person who's gonna get the second bug, and I'm sorry, I'm too lazy to file the bug, but someone can do it, that'd be great, I'm guessing that the way the diagnostic is implemented is it looks for well-known values of 0 in the abstract syntax tree. And in the abstract syntax tree, if you put something else, like a minus or a plus or whatever else, it just gives up. Now, the compiler usually does, it won't do propagation of values, right? Abstract interpretation or whatever else is for the optimizer to do later, all of those value prop and everything. But it does do const expert propagation on the front end. So Clang refuses to do diagnostics that would require the optimizer, but const expert happens in the front end, and that's fine. The problem is it probably doesn't do const expert evaluation of the parameters at that point because it just doesn't want to. Maybe it takes a bit too much time to do that. It would take time to do it. And so it just looks for very obvious values of 0, and then just says, well, this is -0, it's not 0, so I'm just not gonna go into that AST node, and then I'm not gonna diagnose for it. It's the smallest of compiler bugs, probably doesn't matter. But yeah, the problem now is I get this. Right? Who saw that bug? That's another bug, right? So what's the problem here? It's not a compiler bug. Int is 4 bytes, and char star is, in this case, 8 bytes, right? And in every modern system. I'm sorry for anyone else who doesn't have modern systems. But yeah, obviously, char star and int aren't compatible. I can't bitcast from one to the other because they're not the same size. If you remember, that's part of the bitcast. As of my memcopy, you got a memcopy to and from the same sizes. So how do we fix it? Well, first, let's go back to just using bitcast, right? Because like let's not use the built-ins. We want to be clean code. We were talking about that earlier. The problem now is I get the diagnostic, but it's not as nice as when I use the built-in, right? Because remember, the implementation of bitcast is with concepts, and I get this spew of stuff, and I don't have, like Bryce did in his keynote, machine learning to help fix that. So I got to read through it and say, oh, well, like there's these things there, and then like that matches to this thing, and that's why it's not working, right? There's a bit of stuff to go through, but it's a decent diagnostic, and it does tell me, char and int here. It does say, like, because size of char star is equal to size of int and evaluated to false, right? That's a pretty good diagnostics as things come. Just not as legible as the one-liner I got earlier. But that's the beauty of built-ins. You can just have code that gives you the diagnostic. So when you see a diagnostic in Clang or GCC that's just terrible, completely legible, but it's generated for a built-in, you know that someone was lazy in implementing the built-in. Whereas you know that whoever implemented the built-in for bitcast was not lazy and gave you a nice diagnostic, right? They went through the effort of doing that. That's nice. Give a coin to your compiler developer. Okay, so what are we going to do next? Well, to fix it, I'm going to do this. Aha! I have my smart pants on, right? That fixes the problem beautifully, doesn't it? Does this compile? mumbling, it's after lunch, I don't really know. It totally compiles, yeah. So we're gonna run a.out, which is the name of the executable we got out of this, and it says a.out terminated with signal sig seg v, address boundary error, seg v, and we party, this is great. Is that what we wanted? Yeah, I mean, I don't know what I wanted out of it, but we got it. So it's pretty good, it's pretty nice. What's that? What's the sig seg v? Right, we're having fun here with an interview question as an anchor to have a discussion between us, right? So that, okay, we're done having fun with this thing, so what's that thing? Right, what does it do? Well, let's talk about the code. Like, now that we're running the code, let's not just talk about the code, but the effects of the code. What is that thing? Like, you know, like there's this x86 segment, something, mumble, whatever. Yeah, so we could end the interview here, and then I found the boundary of my own knowledge, which is like there's segments in x86, 32 thingy, it bounds stuff, right? Maybe something. I don't know. Okay, well, let's go back. We had a suggestion earlier, right? The suggestion from the compiler, which we have to honor because we're nice people, was please consider using volatile instead. All right, any feelings about this? Denial, anger, no? Well, like, you know, volatile here, my intent is just hands-off compiler, right? And I'm pretty well grounded in standardese to say generally volatile says I'm going outside of the C++ abstract machine, right? Like that is a legit use of volatile, and you can believe me, I'm an expert in volatile. Okay, cool. So this does, and the compiler told me to as well, right? So that's like, you know, compiler told me to. It's pretty cool. Okay, cool. We're going to run this, right? This code compiles, it runs. A.out terminated by signal sig seg v, address boundary error, sig seg v. Woo, good, nice. Are we satisfied with this? How are we feeling? Yeah, Matt's satisfied, nice. Well, does it always do that? Like, I don't know. Yeah, maybe? No, I see some heads nodding. Huh, okay. What does my slide say? Actually, no, good job, you got it. Cool. So it depends on your perspective, right? So we talked about different perspectives without me calling it out. But, you know, language, compiler, people, instructions, other perspectives, hardware, operating system, hypervisor, something like that. There's a lot of perspectives to be had in terms of what this ought to do, right? The language might say something, but the compiler might think something else. People obviously have feelings about it. I'll say people's feelings don't really matter in terms of what the code does, but whatever. The operating system might think something else, the instructions, the hardware. So, you know, there could be different meaning. And really, we've only just focused on language perspective, and we've sprinkled some people perspective here and there. But, you know, like volatile says, just hand off my code, right? So, you know, let's do some pseudo assembly of what that actually does, right? Because I like pseudo assembly. Right? So this 0 here, you store the value 0 into register 0, store the value 0 into register 1, and then you store into R1 the value R0. Right? And this is just do what I mean, is my intent with using volatile. Right? And that's a valid intent, I think. Right? Like, you just want the compiler to do whatever you mean, and the hardware to do that, and so on. And this is pseudo assembly that I think is what ends up in most programs. Right? Okay, cool. Really though? Like, does it, your intent is do what I mean. Does it actually do what you mean? Well, not really always. Like it won't always, if your intent is to get a trap, it won't always give you a trap. Now, why is that? Actually, like, let's step back a bit. What does volatile mean besides just hand off the compiler? Any clues? Talk to hardware, yeah? External behavior, make no assumptions. Yeah, so I have a list. Signal handling is good for volatile. Untrusted shared memory, infinite loops, set jump, long jump, avoiding speculation, external modification, do what I mean. Control dependencies also. So I wrote a whole thing about this. You can go read up. But volatile has legit uses, and like this is kind of one of them, right? External stuff. is happening. But really, like when people get handed volatile, the feeling they get when you're a new programmer and you get given volatile is this. I think, well, new programmers won't know what I'm talking about. I'm sorry. I'm really sorry. But I'm not sorry, actually. But the older programmers will know what I mean by this, right? Like you get given this volatile sword and you're at the start of your experience as a developer and someone tells you like, it's dangerous to go alone, take this. And then they tell you nothing else. And you gotta figure out what you have to do, right? That's the game that you're playing when you do volatile. Right, so now that we've talked about Zelda, this is a Zelda reference for the kids here, Zelda 1. We're gonna talk about Zelda 2. So actually, what happens in Zelda 2 is you get told this instead, right? Now, everyone in the room knows what this is, right? Ore no na wa era desu, right? Yeah. So people thought it was a hilarious meme when they discovered this in Zelda 2 because the translation in English was I am error. And people assumed, they assumed that that was a weird translation from Japanese to English when in fact, like this is just era, right? So basically when you're handed volatile, you're just handed a tool to make errors as Zelda has shown us, right? So this is the history we've learned from video games, or at least I've learned from video games. And that's my view on what it is to hand out volatile car start to people. Now, let's talk about this though. If you're familiar with C++, there's this concept of objects living at places, right? And when we're casting 0 to volatile car start, what's even there? Is there a thing at 0, right? Like C++ is all about objects, their lifetime, where they live, and the effects on them. And my feel when I see this type of code is it's not a place of honor, there's no object there, right? Do you all agree? No, you know I try to trick you. By now you know. There might be something there, right? Like in the C++ abstract machine, there totally isn't, but we're doing volatile. There could be something in there. So what could there be? Well, there could be a memory map register, there could be an interrupt vector table. This is not theoretical, right? Like memory map register here at a low address would be like a VGA graphic card or something like that. So I'm writing black into the VGA graphic card at a certain location. Or the interrupt vector table in x86 real mode. There's a 256 entry table at address 0. And fun fact, the interrupt pointer at that address is the divide by 0 handler. Beautiful, beautiful. Right, so if you're in x86 real mode and you write at this address, you're dealing with the divide by 0 handler. That's beautiful. So is there something at that location? Well, it depends, right? It depends. It could be something related to graphics, could be related to other stuff. Memory map registers are great. What else could there be? Well, there's a thing called WebAssembly on the internets. In WebAssembly, when you write to 0, there totally could be something. Right? There's no memory protection in WebAssembly, so between 0 and the user stack, there's nothing, and so that write just works, right? There could be memory protection, in which case you get a trap. That's great, right? There's nothing, but it traps. Okay, cool. So even without an object, there's something going on. Okay, cool. What else is there here? Well, we're really kidding. It's fine. We like it. But, I joke, but what's memory protection? Mommy, Daddy, what's memory protection? So we're gonna have to talk about memory protection now. So protection is important, and basically it's about virtual versus physical memory addresses, right? So physical memory, I'll just say it's DRAM. I'm hand waving here. If you're not happy, comment on YouTube, I don't care. But virtual memory is like a process's view of memory. Right? So the process has a view of what memory is, and that's a virtual memory, and then that maps somehow into physical memory that's kind of DRAM. Right? Each process has a different view of its address space. Now, I'm generalizing. It's not the case in everything. Like in DOS, you don't have that concept. Everyone shares an address space, and old Macs as well. But we'll just assume that you have processes with their own address space, virtual, and they map onto a shared DRAM somehow. Right? So the process view of memory is kind of arranged? No, it's not. But what is it? It's a span? Is it a span? Well, I don't know. Like that, maybe my knowledge breaks down here, right? Maybe I'm going through this as a way to see like, oh, hey, like I understand memory and stuff, but it just kind of breaks down here. Just slap it down, it's gone. So, okay, what is it? Like, it's a bit frustrating, right? What could it be? I'm gonna say something and you tell me what you think. I think it's kind of like an ordinary map. Is that right? For those in the back, what? It's too small, right? Yeah. Well, I'm gonna have to say it out loud or write it bigger. Let's write it bigger, and I'm not gonna say it. I'm not gonna read it. It's a thing with no honor for me to do that to you, but I think it kind of is like that, right? So memory mapping from virtual to physical is kind of like that, which is funny. It's in direction. It's great, right? So can you imagine that you're running your computer and there's an unordered map under the hood just doing stuff, right? That's great. Like, what are the ABI implications of that unordered map, right? Who would put an ABI in this and have to make it stable? Do you think this would be a good idea for your computer to have a strict ABI for an unordered map to run everything related to memory? Who thinks the computer does that? 2 people. All right. I saw a third hand. 3 people out of a lot, yeah. 4th, they're kind of scared to raise their hand. Because we like to talk about ABIs with C++, and we know that the stood unordered map ABI is kind of a problem, right? Because it makes it so that unordered map is kind of slow because you can't change the hash table for a bunch of reasons. And so it has kind of older and slower ones, or sorry, the hash algorithm. But let's look at this a bit more, right? So we'll write this code. So basically, virtual to physical kind of takes your process ID and an address, right? You're trying to map the address from virtual to physical. It'll return what I call the PT, a page table entry, which will contain something about the physical address and other metadata information, some things. And I use optional to represent no entry, right? So if there's no entry at the address that you've put for that process, it'll return the optional being empty. Otherwise, it'll return to you a page table entry that tells you the address in physical memory. Make sense? And a bunch of metadata about it. Right, that's sensible. That's what our unordered map does, right? So vert to phys inside itself just has an unordered map that does this, it does a lookup, right? Sensible. That's how memory works most of the time. Okay, cool. So let's draw it, right? So I have this virtual memory. So in this case, I decided to just draw 32 bits because I'm lazy. So you go from 0 up to 7 FFFF for virtual memory. And on the other side, you have physical memory, and I don't know how much RAM you have on your machines, but I don't have that much on my 32-bit machine, so it goes up to there, right? So you have a bunch of virtual memory for every process. Every process has one of these and maps onto that, right? That's what the unordered map does. That's what vert to phys does as a lookup. And when you do a lookup, each page in my example is 4 kilobytes, kibibytes. It could have been other sizes, right? So I'm not gonna talk about huge pages and other stuff, but you're gonna do a lookup of this address here for this process here at this location here, and it's gonna return a map into this physical address, right? And so when I dereference 0, it goes up to the top, tells me where 0 in the virtual memory lives, and maps it onto the physical memory. Wonderful. It makes sense? Yeah. Or it might map it nowhere, return a stood optional that's empty. It might return something about memory protection. Remember we talked about protection? Protection is important, and I didn't explain what it is or why. And in general, physical memory is usually belonging to a single process unless you love a map and you share entries between different processes, right? That's another fun thing that we can talk about. I won't say anything about it further. Okay, cool. That's neat. I like it. Okay, so now we have this vert to phys thing, right? And I'm going to hand wave a lot more because we have limited time, and I, if I try to explain how everything works, every computer is beautiful and different, and they all work differently. And so I'm going to explain a subset of how they work and overly simplify it because we don't have that much time. But so basically, PT, the thing I'm returning, kind of looks like that. And again, if you're on YouTube, you're really angry at me. I know I put this thing called other bits, right? And I'm not gonna talk about dirty. I'm not gonna talk dirty at the talk. I'm not gonna talk about modified. But if you're angry in the comments, just put stuff there, it's great. I'm not driving for engagement, by the way. I'm just gonna delete your comments if they're angry. Okay, so what does this do? So I decided that in my page table entry, which again, super hand wavy, this is what's there. Now, you have the physical address, right, which is 38 bits in there. You have the page offset, which it's not really in a page table entry, so let me have it, but it doesn't actually make sense. But there's this other metadata in there, right? Now, we talked about protection earlier. That's the protection. Now, again, not every computer works like that. I'm oversimplifying. But when you look up an address from virtual to physical, it also tells you if you have read, write, and or execute accesses, right? Hand wavy, it's not always like that it works. But in the case of *** 0 I'm dereferencing and storing into that location. And so if I don't have write permissions to it, it's going to fail, right? That's what this metadata tells me. The computer is going to look, say, I know where you're trying to write, and you're not allowed, right? Or it could return an empty optional and say, well, there's nothing there, so obviously you're not allowed to write. Or if I tried to read from it and the read permissions weren't set, same effect, same thing with I tried to execute from it. Make sense? Yeah? Okay, cool. And then there's this other thing that I want to talk about, which is present, right? So this one is kind of like if you had a page table entry, you go there, you go, finally I found it, and you have this mushroom that's like, thank you, page table, but our page is another storage location, right? Again, sorry, video game references from the 80s. Sorry, not sorry. But you can have fun with these page table entries and other stuff. And in this case, some platforms do this where they say, actually, I'm going to put a page table entry, but I paged it out to disk or something like that, or to the network or whatever, right? And so it might say, yeah, I know about this thing, but it's not actually in memory. So OS, before you go back, refill the thing into memory, and then do a page table walk again and tell the process, actually your memory is here, right? So it's longer latency to refill the thing and whatever else. All right, makes sense? Cool. So what does it look like? So I want to implement this vert to phys thing, and I'm going to implement a hash table lookup now. Are you ready for this? Because it's going to be beautiful. What does it look like? Right, this unordered map lookup. You're going to love it. I guarantee you're going to love it. It's beautiful. It's amazing. Who likes magic numbers? Okay, so what's special about these 4 numbers here? What do they have? They're consecutive bits in the address that I'm trying to look up, and they're all 9 bits, right? And so what I'm doing is I'm extracting 9 bits at a time, right? So if you remember, I said that my pages were 4 kibi bits, right? So the first line here, FFF, is getting 4 nibbles out, so that's 12 bits, right? And after that, I'm segmenting the actual address into 9 bits at a time to do a 5-way lookup into my map, into my unordered map. It's this 5 levels lookup, unless you want to add a hypervisor, then we'll have another level of lookup. I'm not talking about that, but it's wonderful, right? This is how, at least on x86 64, AMD 64 stuff, this is how it works, for real. So this unordered map works this way. And what's wonderful is, you remember the question I asked you, would you make this ABI inside of your hardware? It is ABI. Fun fact, the kernel has a contract to honor with the hardware to do exactly this. Right? If you look at the manual for your hardware, some hardware has guarantees about what the layout is of that unordered map and what it looks like. Not all of them. Some of them support page table walks fully supported by the kernel, and the hardware doesn't do anything there. But some of them force you to have a certain layout. So what does it look like? I'm going to draw a picture, and you'll find that picture beautiful, I'm pretty sure. So I took all these offsets that I calculated to show you where they are. Because remember, I took 9-bit offsets and then the 4 nibbles, and this is roughly what it looks like. Inside of every piece of x86 machinery, you have a page map-based register that's relevant to your process ID. This is called the register CR3. And it points here at where the start of your page map is for that specific process. Right? And you have other page maps down and up from this. And then you take the offset, the nine little bits that you calculated, you know where the entry is, and it points there, and then points there, and it points there. And so every process shares these things. Finally, you find the base of your page, and then you were trying to dereference that address, and that's the page offsets, right, the 4 nibbles, and that's it. That's where your physical location is. Cool, so that's how our ABI works. We just have a page table walk. And so when I do ** 0 = 0, And if there's a mapping in there, I'll do a walk and I'll find a page at address 0 that might be completely somewhere random inside of physical memory, not at 0 necessarily. And I'll try to dereference it. I also get the metadata bits, or read, write, execute, and I might be told this isn't readable, this isn't writable, or I might be told something else. Cool. Any questions? No? Cool. Great. All right. So what else can we talk about? Well, wait, so I have a question now. Every memory instruction is a hash table lookup? Like, how often do you hash table lookups in your code? Not too often, because they're kind of expensive, right? And I just told you that every memory instruction that your computer does is a hash table lookup. Does that sound right? Sound fast? That's how it works. It just is, right? But it's even funnier than that. It really is. It's not that funny, actually. But stuff kind of works this way. I find it funny, but I'll be nice. So what's interesting is there's basically like 3 kinds of instructions, right? There's arithmetic, there's control, and there's memory, right? Arithmetic is like plus, minus, multiply, divide. Control is a jump or a test or whatever. And then memory is load stores. Load stores are about 2/5 of all of the instructions, right? So I just told you that there's a a hash table lookup for every 2/3 of your instructions. Does that sound right? Yeah, it sounds right. I see you saying no, but it's right. It's correct-ish. And the other thing is all those instructions are in memory, right? Thanks to von Neumann. It's a von Neumann architecture compared to a Harvard architecture. So all the instructions themselves are in memory. And so every time you execute instructions, you do a hash table lookup. Maybe that instruction is a load or a store. 2/5 of them are, in which case it's also a hash table lookup. All instructions are memory accesses in themselves. The page table itself is in memory, usually. And so when you walk the page table, those little steps I showed you in the drawing, that's also memory accesses. And the hash table lookup is multiple accesses, right? Because there are multiple levels, each for 9 bits. And some instructions are multiple memory accesses as well. So x86 has, for example, rep move SB, also called memcopy. And there's ARM that has LDM or STM, called push pop. And they can trap part way through the execution. So you can do a memcopy of like 1,000 things, and that's 1,000 memory accesses, plus the memory access for the instruction itself, plus the memory access for the page table walk for every single thing. What are we talking about again? Okay, so hash tables, they're everywhere. They're awesome. It's gotta be slow. How does it actually not slow down? It sounds recursive because the page table is in memory and like that doesn't work, right? Does the page table? So you can page table while you page table? That's, how does it work? Oh, I heard a thing. I'm not gonna repeat it. Okay, cool. Okay, so what's the solution? Ready? You ready for it? This is the moment. This is the moment you've always been waiting for. You ready? Okay, count with me. Let's count from 3, okay? 3, 2, 1. Oh, that's great. It felt awesome. Caches, yeah. So caches make it so that all this stuff that I described work. And again, I'm hand waving. If you're angry at me, it's fine. It's fine. We only have a little bit of time. But there's a lot of caches to make this work, right? So thank a cache when you can. Yeah, so hardware has physical wires that perform some lookups, right? The caches are kind of all these cool little things that have wires. And it's kind of a fancy Rube Goldberg device. Like when you look at hardware, it's like these things, and you think it's digital, but it's actually analog, and the signal kind of settles over time, and it looks digital, and they propagate. It's really cool, really cool. There's a lot of them. Yeah, awesome. This is how everything works. Nice. Okay, so let's draw it. And again, artistic liberty here. I'm doing box drawings with ASCII on a terminal. So like, don't hate me if you don't like the drawings. So how do machines work? Well, they have registers, right? We know about registers by now. And we're gonna try to show some of the stuff that they do, right? So you have these registers, 0 to X, let's call it X. And then in a hardware, fairly often, you have these shadow registers, right? That allow you to have more speed, right? There's a register renamer that renames your registers as you execute. Didn't you know? The registers have secret names. Shh. There's usually more shadow registers than our real registers. It's great. It allows you to do a lot of speculation. And then there's this great thing called IP. It's special. It's special. It's actually the instruction pointer, PC, whatever you want to call it. It's special. It's really special because it's an instruction pointer, and it points to the I dollar and the D dollar. Is it dollar? No, it's iCache and Dcache. Sorry, it's like the cool person parlance. So iCache and Dcache. You know, dollar sign is cache. It's funny. If you see iCache and Dcache, it's spelled that way pretty often. And IP points into the instruction cache to know what the instructions are to execute. So that's a cache. We have two caches. That's the L1 cache. Let's call it that. And again, oversimplification, sometimes between IP and I dollar, there's other caches as well, right? There's the decode buffer and other stuff. There's also like a huge checkerboard of instructions that are in flight so that you can kind of have full parallelism in your instruction level parallelism. So the shadow registers are used, and when a shadow register is fulfilled, it dispatches instructions and other stuff. You know, there's books that explain this, but just going to ignore it for now. There's more caches, there's more machinery. But then, you know, just these caches are really small, right? So what do we do about caches? We have more caches. Yeah. So level 2 cache, much bigger, much nicer. So another I dollar, another D dollar. So iCache, Dcache. So the instruction cache sometimes, usually is smaller than the data cache. Sometimes there's the same thing, right? But I'll just pretend that they're different because usually they are nowadays. And we can put more caches, just more. If you look at the die shot, there's caches everywhere, right? So we're just going to shove more caches in there. And then, you know, we're going to stop at 3 caches because I'm kind of running out of space. And so I'm going to represent memory here. So these caches go into memory. And memory is big. It's really big, right? The caches are like megabytes. Memory is gigabytes, right? Great, awesome. And so where's this vert to fizz thing that I had? Where does it live? Right, so I said there's the page table walk and all the other stuff. Where do you realize that you got to do a page table walk and all this stuff? It's in the register, it's in the instruction pointer, the L1 cache, L2 cache, L3 cache, memory. No, over there. When you get to the network, disk. TLB. Oh, I heard TLB, translation unit. Okay, cool. Well, in my example world, L1 and L2 cache will be addressed virtually, right? So when you take a pointer, it's addressed virtually in my world. It's not always the case. And then the rest would be physically, and so the translation has to happen here. And so you do a lookup with those magic, beautiful Rube Goldberg wires that I explained in the level 1 cache. If it fails, it looks in the level 2 cache. If it fails, it goes and it does a TLB translation. Translation look-aside buffer. And if it hits, then you do a vert to fizz because you have a hit in the TLB. So you just do a quick lookup. If it fails, then you do a page table lookup, the little drawings I had earlier, and that might cause a seg fault to happen here, or it might return an actual address. Right? So seg faults happen here. So again, star car star 0 equals 0. If it seg faults, it'll probably seg fault here. Right? Or it might seg fault later. All right. So this is roughly correct, but more caches. Right? Now, there's other stuff to notice, like, you know, here you see the executable bit. You might check it here in the L1 instruction cache, say, can I execute from here? Or you might check it when you fill the instruction cache, because you know the instruction cache's purpose is to execute. And so if you try to fill a thing that's not executable, you might just mark that entry as invalid and then not look at the executable bit. Here, when you try to read or write from the L1 data cache, you might say what happens, or you might have some read through or write through, whatever. Here you might have, so when you go from addressed virtually, addressed physically is when the processor or the hypervisor matters, right? Because each process has to have its own view of memory. And if this side is addressed virtually, L1 and L2, then each process has to have different entries into the cache. Right? Unless they share pages and the TLB lets you do that and whatever. So they have different views of the caches, different entries in it. Okay, cool. And again, like this hardware imposes ABI on the OS. Cool, it's awesome. Okay, so let's have some fun. Let's shrink this a bit. I didn't put any other dollar signs in there, sorry. Okay, so let's make it more fun. So this is how roughly hardware works. Yeah, I'm really hand-waving here. But hardware doesn't actually just always execute like that. So what if I run this under GDB? That would be cool. right? What happens when I do that? Well, we could talk about it. But GDB has to be able to debug things. If I have a reverse debugger, the reverse debugger has to be able to reverse all these things, right? So it has to capture the architectural state, be able to unwind it and advance one instruction at a time, do a bunch of stuff. So it has to have a bunch of cool stuff that it does. But you can do more cool stuff. Like you draw a box around this, and then you all know Valgrind, right? So Valgrind has this cool tool that comes with it called CacheGrind that allows you to simulate the caches. You could do that too, right? So you can run a whole fake hardware inside of CacheGrind to simulate how the caches work and see all that beautiful stuff executing. So you could, in CacheGrind, in GDB, run star car star 0 equals 0. And then, like, that's your weekend right there. I know I'm old-ish, but, like, that's a beautiful weekend. If you see that in action, amazing. And then, like, you know, you can do other cool stuff. Like, you could just run this inside of QEMU if you wanted to. QEMU is great. You could run the whole thing inside a hypervisor or whatever. It's great, right? I like fun. You like fun? Yeah, you're still there. So, I guess, yeah. Cool. Okay, so let's go back to our code here. Nice. I'm not a fast typist, I'm sorry. All right. So what does this code even do? Right? Like, talk to me about the code. What does it do? Well, it really depends, I think, is what we've discussed so far, right? Like, it depends on a lot of stuff. Is C a direct mapping to hardware? Not really, right? Because it can get optimized out. So people who are used to C get really angry at this code because the code gets optimized out. C is not a direct mapping to hardware. But what do you believe it does, right? What does this code do? It makes you believe things, right? Those things might be wrong, but it makes you believe stuff. And what does the language spec say? And importantly, I know I share the evolution of the C++ language, but does the language spec matters when reality is on the line? Not really either, right? So what does the language spec say? That's a good question to ask. But if you disagree with it, maybe you go argue on RCPP or something, but like it might not be correct. So maybe we need to change the language spec in some cases. And what is even hardware? Like I've described a narrow subset of what hardware exists out there, but it's not what every hardware does, right? So do we really care? Like on some weirdo hardware, it might do something different and completely exciting, right? But here I'm really talking about like some of the programming side of what the stuff does. But there's also another aspect to consider here, which is the human side of it, right? I asked you a question, what does it do? And some of you, it provoked revulsion, right? But I know it's a bit of a one-sided discussion, but it can cause interesting discussion when you talk about this. I've had a lot of interesting discussions about this code. It tells me if you've looked under the hood, right? If I'm trying to hire a systems engineer, like low-level kernel person, a compiler engineer, they kind of need to look under the hood, right? So as an interview question, it's a nice warm-up to see like, hey, pop the hood open, what's in there, like close the hood. It's a good way to see that. And it also tells me if you can explain what's going on, right? Like if we're interviewing you for a role that needs a lot of communication with other people, right? You're not just coding your thing and your code goes into a vacuum and nobody looks at it ever again. If you can't explain what you do, that's a bit of a problem. If you're an expert in this field, right? Not everyone is. You should be able to explain at least some of this. And you should be able to tell me like, oh, I don't know. Right? At some point, you hit a limit of your knowledge, and you should be able to tell me, I don't know. So what does this code do? It does a lot of those human squishy things as well, which is kind of neat, right? All right, cool. Well, this is the code. It's fading away now. I think it's probably the end of the talk, because it's faded away. Yeah, cool. Well, code's still there, though. Huh. OK, well, I'm JF. So as I said, I work at Woven Woven by Toyota. I chair the C++ evolution working group. This has been my talk, star car star 0 equals 0, semicolon. Semicolon's important. So you know, here I'll say arigato gozaimashita. Company forcing me to do that, have to say in Japanese. So we have woven.toyota is our website. We make mobility software we're hiring. We have places in Tokyo, Palo Alto, Seattle, Ann Arbor, Brooklyn, and London. Drew a beautiful little logo here. That's pretty much it for the talk. Thank you.